I have just drafted my talk in very generic term, not in any very specific to the list. So whenever you have any queries, please you can interrupt me in between. I mean, I want to make it a more interactive one. Not like an end of, I mean, you may have questions in between also. Please interrupt me whenever you feel that this is not clear. So. Uh, uh, we more focusing on the our ISRO efforts in terms of the our own the first kind of this is our onboard payload, which is what we call it mission E08. So basically, it's a term what we use now as a technology. E08 is Earth observation satellite. So the E08 is the latest mission which carries GNSS-R, one of the two passengers on this satellite. And it was launched in the last year, 16th August 2024, from Kota using SSRP D3. So it is a small satellite launch vehicle. It's very new development from ISRO. And I just put some picture to show you what kind of satellite works and how. And you see the right next to the top bottom, the bottom was with the fully integrated satellite, considering all the power management, all the satellite everything. Can you go to the next slide? Okay, I just today my perspective about myself actually. Already a lot of introduction has been. When I go through the background, I have done my UG from in BTech in Electronics Communication. And then I'm taking RF and microwave. So basically, by training, I'm a radar engineer. And then I ended up with my PhD in agricultural of soil moisture during my service period. Currently, my role is basically I'm leading the NSR mission as a science member. I'm one of the core science member of an NSR mission, which is almost about to launch in the mid June this year. And it's one of the first global mission with dual frequency radar. I'm leading the soil moisture, lead of the soil moisture. Basically, we are going to produce a world first 100-meter soil moisture lab for India as a global target. I have also been associated with EH04. So basically, we have our own sequence starting from R1, 1A, and now 1B is also coming in this year only. So hopefully, in this May, we are going to launch this R1B, which is the EH09. So I'm associated with the science lead of this mission. The next is the science lead of EH08. It's our refractometry. So here my goal is to develop the algorithms to retrieve the soil moisture from refractometry over the land targets. And yes, I'm also on the technical development programs of the ISRO multiple missions. My responsibility is about development, operational product development for the different users, tools and techniques, and I also work a lot of R&D on the sensor diffusion studies for future technologies, considering SAR, radiometers, and spectrometry as well as the interferometrics. So, in outline, basically, I will be covering the basics of particle remote sensing because a lot of participants are not from the particle remote sensing background, so I will just flavor what is the particle remote sensing, which band to use, and for which applications. So I will just give you a very shallow. I will go to the particle remote sensing basics. Then I will go to the soil moisture, the compositions, what are the methods are available for soil moisture measurements, including in situ measurement from satellite, from models, and then some of the micro sensing techniques based on the different sensors like SAR, reflectometry, and millimeters. And then measure techniques and closure. And then I will jump to the basic GNSS-R. So I think from the first day, lectures from particularly, they have made my work much easier. They have almost covered the basics and principle of the GNSS-R. So I will go very fast in that basics of configuration. And I'm more focusing on the other user rate microsite mission with GNSS-R payloads. What data products are available for the user community, and then little bit detailed I will talk about the our scientific table algorithms, what we have developed in our team, and then result and management. So basically, I will show you some initial performance evaluation of our own GNSS-R data sets regarding the scientific table. So as the study Garrison already has James already covered this microwave band. So basically, we have a electromagnetic spectrum, and most of the part basically we work in microwave domain. So there are different bands. Sometimes for a non-remote sensing person, they get some confusion about the why there are so many bands out there. So basically, each band has their own merits and demerits. So as per the application requirement, we use the band like currently the Dr. Garrison and Rashmi, they basically both mainly work with the P band because it has longer wavelength, deeper penetration, and other advantages. Most of the Jesus satellite systems they work in actually L band. So this band is basically this is the band which is mostly navigation satellite we use, considering the GPS, Galileo, our own ISRO Navig satellites. So these are the bands. Yeah. So this is a band basically defined by the convention. So we call it P, which is 300 megahertz. Then L band, S band. So this is the range actually where you can have multiple bands or bands within that album. Like if you consider the cases system satellites, they have their multiple subbands like L1, L2, L5, and they are separated by some kind of some band gaps. And the frequencies are there as per the thing. Okay, so advantage of microwave something. So basically, there is a very distinct advantage of microwaves as far as the remote sensing is concerned. So I have just listed down the what advantage we directly gain from as compared to the optical and other remote sensing satellites. So basically, it's an all-weather capability. So because it has its own source, so it doesn't depend on the sun or the source of the transmitter and also it doesn't depend on the clouds. So during cloudy season, also you can have observations which is very difficult to get from the optical camera. So during like you know the India, most of the part during monsoon season it is mostly cloudy. So in that time basically you mainly depend on the centimeter radar data, which has a very good capability, and you can observe under cloud. You can also observe the different land and targets. Then the day and night operations, I told you we have our own transmitter, so we don't depend on the sun or any other sources. So we can operate in night also. Then there is no effect of atmospheric consequence. So that is one of the advantages. And the most important from microwave is that it is very sensitive to the dielectric properties of the medium. So whether it is the soil, whether it is vegetation, maybe any kind of targets, after the microwave it will be very sensitive toward the dielectric properties. So basically, when we derive some information from microwave satellite, the major parameter is dielectric constant, which always has one of the basic observations. Then sensitive to the surface stiffness, like which is linked with the ocean wind speed. So a lot of microwave satellite considering the scatometer, SAR, they are capable to derive the ocean wind speed directly from the ocean observations. Then element of distance, that is electromagnetic, is another mode of microwave electromagnetic mode, which is capable to derive the surface information in terms of the changes what is happening within a month or within a day. Then there are a lot of advantages of that. And the last one is the subsurface penetration, which is very important. Like if you target the room soil moisture at a deeper layer of 40-50 centimeter to 1 meter, in some cases, like except microwave, there is no band which can go deep at this soil depth. So basically, that's why that is the reason the microwave is the most optimum band for the soil moisture at deeper layer. There are different platforms. I'm just doing this faster. I'm just to purpose to show you the same sensor we can fly at different platforms. So starting from the space bomb and aircraft based and ground based. So basically, whenever we design a new sensor for the to cater to the requirement of multiple applications, actually we start from the ground base. We first develop the prototype from ground base, then we test it over the drone or maybe aircraft base. Then we can go for the mission for the space bomb. So this is the kind of a, you can say like modus operandi is there. We follow this philosophy that we have to test with the algorithm, test the sensor performance at the ground and air bomb. Then we go with the space bomb satellite development. Then there is different kind of sensors, active sensor depending on the. So basically there are two types of sensors: passive sensor, active sensor. So passive sensor basically doesn't have any its own sources. Okay, it always depends on the sun or some other measurements. And active sensors basically they have their own source. They transmit a signal and then receive the reflection from the target. So that is we call it active sensor. So in microwave, the majority there are two kind of categories are there: active and passive. So always just remember that active is it has its own sources like a centrifugal radar. Radar always has a transmitter as well as a receiver. So it comes under category of active sensors. I have just put a just brief glimpse of the what are the different sensors are in the two categories. So if you consider the active sensors, basically the major part is the temperature radar systems. There is altimeter, altimeter and ground magnetics radars. So these are the radars which has a transmitter as well as receivers, and they use this transmitter for the measuring the parameters. In passive sensor basically doesn't have source actually. It just can receive whatever coming from the reflection from the ground or maybe any kind of emissions like radiometer. So radiometer is the most sensitive receivers basically to receive the emission from the Earth's surface. So that is like we have a sounder. Sounder also is one of the passive sensors which measure the temperature and humidity of the atmospheric profile. And then comes the laser refractivity. So basically, refractivity, as you know, we just receiving the reflection from the uh, uh, transmitted signal from the reflection from the ground, which is being transmitted by the GNSS satellites. So it is also one kind of a passive sensor. So here the black color we have a transmitter which transmits electromagnetic pulse for a given frequency, and then the antenna will radiate the signal for a given targets. And then we receive the signal through the antenna, and again the receiver will receive the signal, and then we go for further processing to get it to form an image in case of the temperature radar, maybe spectrometer or other. So this is just showing the animation how radar transmits and receives the signal. So basically, we have the radar. The basic definition of radar is radio detection and ranging. So basically, what we do, we transmit a electromagnetic pulse, which is very sensitive towards the target, and the microwave energy is transmitted and which is scattered from the target. So suppose there is a target which is far away from the radar, and this radar transmits a signal by this one, and then there will be a scattering of the targets. So whatever energy coming back to the signal receives, and then it finds what kind of a ranging is there, what is descent from the target from the transmitter, and then we further we do the processing to generate the images, radar images, and then further processing. This is one of the this we did the animation actually. I just in the right side I put an animation to know how the images are formed actually, how the sound images are formed when you the satellite moves from the just click on this right side play button is there. I'm not able to do. Just, just yeah, click on this. Yeah, just click on this image. So basically, my purpose is to show you the how when the star moves in the orbit, how it moves, and then we generate a very high resolution star images. We do a lot of star processing, which is done by digital processor actually. We don't, I mean, we collect the data. So this is the one of the example of the strip map mode where the star is moving in the orbit for a given altitude, and then when it's mapping the area, it is keep on generating the images like the star images. So this is one of the vision. Move forward. This is a receiver actually which receives the thermal emissions from the targets. This is one of the very classical receivers. So basically it's a receiver with a very high sensitivity parameters. So whatever emissions coming from the land, different targets from the vegetation, from the forest, from water body, it receives the emissions and then we get a brightness picture for further deriving the information from the about the targets. So now to come to the refractometry. So I call signals of opportunity because why opportunity? Because it is not meant for the remote sensing purpose. Basically, these are the navigation satellites which transmit L-band signals at a particular frequency 24/7. So always the transmitters are moving in the orbits, and the reflections what coming from the targets like this is the GPS satellite and this is the RF satellite. They keep on transmitting the 24/7 signals, L-band signals. And what we are interested in that, if you have a receiver in the lower orbit, at altitude of 400 kilometer to 500 kilometer or 700, we can see this reflections at this receiver. So this is what we call it. This is reflectometry. Basically, we are measuring the reflections from the land, which is by the GNSS-R and GNSS L-band signals. Now I go to the quickly about the soil composition. Okay, so now the soil composition basically before going to describe about the soil composition, why it is important, I know the basic of soil. So soil is considering the four major constituents. Soil doesn't have just water actually. It has multiple components and it is quite complex information if you see the soil physics. So it has four components. One is the mineral. Uh, And these compositions are also varied with the different kind of a soil type. So this is the typical composition of soil. So for a given set of soil, the 45% proportion of the soil is mineral water. Mineral matter will basically it's a different kind of a, particles like a clay, soil, clay, sand, and cement. And 25% is basically your water. This 25% is water, 25% is air, and 5% is the organic matter. So soil is not just a part of the water. It has multiple components. That's why it becomes very challenging to decompose the soil to get a moisture from the soil. So the soil moisture basically by definition, it's basically we are interested in the how much water content in the soil is there. So there are many ways to define the moisture in terms of the gravimetric or volumetric. So there is no single standard way, but typically in the scientific community, we define the soil moisture in terms of volumetric soil moisture. So for a given volume of soil, how much volume is covered by the water. So suppose there are two conditions. One condition is the dry soil. So basically the dry soil water tank, this is the particles, minerals, and these are these white areas are air gaps within the soil particles. And if you see the water in the dry soil water tank, because of the high potential energy, the water gets accumulated in the wrap toward the soil particles. So in the dry soil, if I decompose and make it simplified, the volume part, the more than 50% is the soil solids, basically minerals. Then the water is volume is almost less than the dry portion in the dry soil, and the rest of the gas. So gas mineral can be air, it can be any gas. In case suppose when there is enough moisture in the soil, the soil gets saturated. So this is the second case when the soil is saturated. Basically, all the air gaps are filled by the water. Suppose there is a just after the dry spell, there is a heavy rainfall. So what happens when there is a rainfall? Rainfall basically what does it start the because of the percolation, the gravity, the water gets drained into the soil particles and the all the gaps is filled by the water. So now we see in the typical case of saturated water, the almost 50% volume is covered by the water. And in this case, when the soil gets saturated, if you add one more drop of water, it may not go inside the soil. So that we call it in area, another thing we call it a runoff action. So whatever water in extra additional water is that can be flow toward the horizontal direction. It doesn't go in the soil. So that we call it a soil saturation. So these are the two extreme conditions, dry and saturated soil, which is defined by the volumetric soil moisture. So our aim is to get this volumetric soil moisture estimation from the satellite. Yeah. So basically, obviously, the question comes why we are so much interested to derive the soil moisture from the satellite, because it is one of the essential, you can say like essential climate variables, which is declared by the GCOS committee internationally by the IPCC, and also it has multiple applications in different domains. So starting from, if you see one of the major is agriculture. So in agriculture, it has to ensure that the water is sufficient, water is available for the agricultural practices, and if there is less water, the crop may damage in the case of very high water stress. So in the case of precision irrigation is very important for the water. So we need a high soil moisture to give the information to the farmers that what time you have to irrigate or you have to not to irrigate. If sufficient moisture is there in the soil, we give a advice to the farmers that don't irrigate it. You can delay the irrigation dates further, depending on the availability of the moisture in the soil. The second is the reduce disease and pest pressure. So basically, when what happens during if the agricultural crop is continuously in the waterlogged area, if it is persist for a longer period of time, it triggers the pest and disease problem in the crop area. So if you have a high soil moisture and information from a satellite, we can see that these are the area which is highly prone to be have a disease over the crop in the crop area. So further measures can be taken. Then it is very important for sustainability and flood forecasting. It is very important nowadays because as we explained, there are two extreme conditions. One is the drought, and is the flood. So drought is just the extreme lowest condition, which is basically defined by the non-availability of soil moisture, and then the flood is the extreme level of soil moisture. And any extra rain, if there is a heavy rainfall after just after the saturated soil, it will convert to the heavy flood actually. So flood and drought management is very important application where the soil moisture give a very good understanding about the triggers of the event actually. Then potential management, which is like I explained you the always we have a tank of water for the agricultural purpose, so we know how much water is needed, how much water is not needed for the different practices. We can have very good management. We can manage our water resources. Then we move to crop yield. So it has very good linkage with the crop yield. So because the crop always need a optimum level of soil moisture from the moisture. So what happens if the crop is undergoing through a extreme disease of water non availability? It always has a very has a negative impact on it. So it has a problem on the productivity. So these are the major applications which always need a soil moisture as a input. Now I'll just listen about the particular applications are there within the soil moisture feeds a very good element, an essential element. The requirement of in terms of the temporal digital resolution is not always same. So every application has different requirements. Like suppose if you want to use the climate studies, so kilometer scale soil moisture resolution is quite sufficient. We have a model, we have a radiometers, which give a 10 to 40 kilometer soil moisture map, which is quite sufficient at global scale. But if you go on the agriculture applications, specific by Indian condition, where the field are really small Also, a lot of multi-crop conditions are there, lot of heterogeneities are available. So, in that case, this coarse scale soil moisture is not sufficient to give any information to the stakeholders. So, what we do, the actual requirement of spatial resolution is that actually could be a typically 100 meter. And temporal resolution is very important. This is a temporal resolution means basically at what frequency you are doing repetitive observation. So in agriculture, typically weekly observations are right because IIT also do weekly this advising to the farmers from the different agriculture farmers. So if I consider one in agriculture, actually we need a very high pressure soil moisture and we need a weekly observation to meet the requirement of agriculture. So there are three basic measurements of soil moisture. So the basic most classical measurement is the ground base. So which we call it in situ measurements. So we use gravimetric methods to go and take a dry soil samples and do the lab based measurement to get a soil moisture. And there are other advanced sensors are available, soil sensors, smart sensors which can measure the soil moisture indirectly from the file. There are then the next level is the models. We have hydrological and surface models which can simulate the soil moisture condition depending on the multiple forcing data, especially atmospheric forcing and land forcing data. This also gives soil moisture at a very coarse resolution. And then we have so all these components are made certificate. So there is no single method which can give you soil moisture which can lead to all the requirements. So basically, depending on the application, we need to decide what kind of soil moisture can be used for the application. Nowadays, globally, what we are going in the direction of integrating all three measurements, ground, satellite, and models, to have a very comprehensive soil moisture with a required spatial resolution and temporal resolution. So that is what we are working towards that future. So this is the in-situ soil moisture measurement. I will not go in detail because time is not too much. So there are some items that direct measurements which we use the gravimetric methods. Now you are familiar with the gravimetric method, but I have some field photographs. I will show you. And there are some indirect measurements. So indirect measurement basically we use a device that is a portable device which measure the soil moisture in different techniques. So there are a lot of commercial sensors are available for the measurements in institute. So we use these measurements also to validate our satellite moisture. So this is the in-situ measurement techniques. This is the example I am going to gravimetric measurement how we do the please yeah. So this is the way basically we have soil samplers. We go to the field and we take a so there will be a can. The can we take the soil samples and then bring to the lab. And then we do the microcloning. So basically we are drying soil to get a weight by weight actually. How much before the drying, what was the weight of the soil sample, and then after the drying, what is the weight of the soil samples. And then just using the basic classical method, we derive how much percentage of soil moisture was available in the soil sample. This is the most classical method and one of the most accurate one. But there are some drawbacks of this method. Suppose you want to conduct a experiment in a very large area. It is a very labor-intensive process. Actually, you need to have multiple teams, very large number of teams required. You need to have a soil samplers. So this is the advantage of now. Yeah. So the next is the props. Now this is the soil moisture sensor what I was talking about. These things are highly specialized commercial sensors which have a prop of the length of around 6 to typically 6 to 7 centimeter. And these props are basically inserted into the soil. And soil moisture measurement. So basically, the advantage of this sensors are there. In gravimetric, you have to go and bring the soil first. That takes a lot of time, and after 10-15 days, you get the soil moisture result, how much soil moisture is there. But this is the most simplistic method that it is like a sample and go. You can have a very quickly within a 1 minute to get the measurements. What is soil moisture in the soil? So typically, we use this kind of sensors to test our retrieval from the satellites So again, so these are the kind of snapshot I think we have a very good soil moisture networks. From ISRO, we are maintaining it at different locations. So this is the these are the fixed station. So it is whenever we have like this is the station for the other side. So there will be this is called automatic soil moisture stations. Inside there will be multiple sensors at different depths. So basically we are measuring multiple depth soil moisture every 15 minutes. And these measurements are basically used to test our satellite-based measurement. So this is just to show you how we install this. So a lot of ground-based measurements also we do to verify our retrievals from the satellite models. Okay. Now come to the satellite-based retrieval approaches. So basically overall there are multiple approaches out there depending on the satellite data and the mission, different sensors. So traditionally, the journey started from the passive millimeters to the multi-passive X-ray, then the dark, synthetic aperture dark comes in the picture. But again, the millimeters are quite coarse. I mean, it gives a fire water at 40 kilometers, which is not useful for agriculture. So, but they're very sensitive. Then comes the SAR, which gives a very high resolution radar images, like up to 10 meters you can get the images. But again, the radar has its own drawback in terms of the scattering properties towards the because of the roughness and the vegetation. Then scattering also is quite useful for the global scale soil moisture as C-band and KU band. Then to get a very high precision and very sensitive soil moisture, the community has the next method is called merging two sensors like sensitive aperture radar, SAR and spectrometers, or maybe SAR plus that we what we call it active passive approach. So basically, the active approach means SAR. We are merging the SAR measurements with the radiometers. So SAR gives a very high resolution, and radiometers are quite sensitive, high sensitive to the soil moisture. So basically, we get a high resolution, high accurate soil moisture from this combination. So ASMAP was the first global mission to demonstrate this active passive combination, and it has the L-band radiometers and L-band radars. But unfortunately, within 3 months, the radar got failed. Now ASMAP has only the radiometer, L-band radiometers. So these are the methods which you have to use. I will talk about the new method, which is actually technically it is not very new techniques, but yes, it takes a lot of time to get evolved and mature at this stage. So refractometry is now the new domain of technology domain where we have to take more efforts because there are a lot of constraint with the traditional remote sensing sensors, especially the sensitive aperture radar and radiometers, because these missions are quite computationally intensive, quite big. You need a lot of resources on the onboard. But refractometry doesn't need much resources. It's a very low cost solution. It just receiver. So I will go and talk about. Okay. So now in the microwave features, basically I will talk about come to the how we go with the retrieval. So before deriving any information from the satellite or microwave signatures, you have to understand how the microwave signatures are varying, how it is get affected by the different target properties or maybe sensor properties. So if I divide into two parts, one is the sensor parameters and target properties. Target parameters. So in the sensor parameter, all the sensors have different frequency, impedance angle, and polarization. This is the basic dependency of the SAR signature. So you can have any band signature depend on C-band or X-band. Okay. So it doesn't mean that all the signatures are having the same frequency at everywhere. So L-band signature look different than C-band, X-band or KU band. So sometimes now people are moving towards the multi-frequency observations, which gives a more fidelity to your retrieval algorithms. The main part is target properties. So in the target properties, there are two kinds of targets are there, like surface properties, which is like roughness, and dietary properties linked with the moisture. Then the land cover is called vegetation or forest. So whenever we have the marking of this target, it gets moderated by the roughness, vegetation or moisture. That is the way to understand the scattering properties of the microwave signature interaction with the medium. I go a little bit quickly so that I will come to the point. This is the dietary property that I talked about. So in the microwave soil moisture retrieval, the basic difference is that it depends on the dietary properties of the soil. So if you consider the dry soil and wet soil, there is a huge difference in the dietary variability. The dry side, the range is 3 to 4. And if you take the water, which has a dielectric constant 73. So water, so in the case of moist side, so this is the right side of the plot which shows the dielectric constant versus volumetric soil moisture. So as the moisture is increasing, the dielectric constant also increasing in that monostatic mode, this monoforce function. And only frequency also. So we have dielectric mixing models which relate the dielectric constant to the different kind of site, because dielectric constant is not just depend on the moisture. It also a function of soil properties like a sand and clay fraction, minerals, what I have explained. It also depends on the soil temperature and also frequency of operation. So we have a well-defined dielectric mixing models which we use to derive the moisture from the dielectric. So in that scale, I will go through quickly how the moisture actually changes with the how the signature gets modified by the different condition of soil moisture. So take a simple equation. Take a simple case. There is a dry soil. So low moisture is constant. So if you transmit a signal which gets reflected from the surface, so reflector wave intensity will be low. So most of the energy will go back in the forward direction. Very less energy, this is total energy, is coming back to the sensor. But if soil gets wet actually, its dielectric constant increases a lot. So once there is an increase in moisture, which leads to the high dielectric constant, and then the energy again, the reflected energy will be more. So this is typical thumbnail. I mean, this is the what relation we found. It's a linear related to the soil moisture and backscatter energy. So the blue block basically is the how much portion of energy getting back to the sensor and getting forward to the direction. So basically, this is simple physics. In physics, what happens whenever there will be electromagnetic signal transmitted, whenever waves interact with the medium, there are basic physical mechanisms like scattering. There will be a scattering, there will be reflections, there will be reflection, and there will be attenuation. So, if this is a dry spell, the wave will penetrate more this side. So there will be less effect. But if the soil is wet, the wave will not penetrate the soil. So penetration will be less, and attraction will be less, and most energy will go back to this is typical physics-driven process understanding how the different conditions lead to the change the soil nature. Now the next parameter which affect the soil the soil signature and radar signature is the roughness. So there are two conditions. This is the habited field, so roughness is not too much, but this is the crop field actually. So crop field there will be surface roughness. So this roughness actually also has a very good impact on the SAR signal modulations. So this is the case of the smooth surface. So in smooth surface, there will be a lot of energy going back to the going in forward direction. Very less reflection. But as surface becomes rough, you see the roughness is increasing. The energy of whatever coming back. So this is the plane mirror like surface. So nothing is coming back to the same structure. But in this case, that surface becomes rough. The energy which is getting back to the sensor is increasing. So typical understanding is that more rough surface will give more energy in terms of the diameters. But this may not be, this should be applied to the refractometry because that is a bicating case. Okay, just keep in mind. You may get confused when you go for interpreting the refractometry signals in terms of the SAR signals because SAR is the most static SAR. I mean, transmitter and receiver are the same place, but in refractometry, transmitter is far away from the receiver, so it is like a bistatic. So in the bistatic, the interpretation will be almost opposite. So there is a drawback, the vegetation effect of vegetation time. That is very important because in the bare soil, only two parameters are important: soil moisture and roughness. But if there is a crop field, the crop get moderate your signature, and the crop get attributed by the signals which is reaching to the soil. So before the soil there is a crop with some height. So what happened? Whenever there is a scattering, there will be multiple signature from the multiple component of the crop. So this get changes your signatures. So what happens if you in case just for example, if you get a high signature over the crop field, It doesn't mean that it is coming from high soil moisture. It may come from the crops height. So that's why the most challenging part here for the soil moisture level is that how to decouple the effect of vegetation from the soil. So if you remove this effect, the vegetation effect, you can easily get the soil moisture with better accuracy. So this is what we have been doing since long to develop multiple models, multiple techniques to remove the effect of roughness and vegetation. So I'll go fast. Okay, now come to my main topic. I have still some time. So I'll start with the basic configuration. Already covered this, but I will repeat it because it's very important to understand the reflectometry domain. So in the reflectometry, there are multiple configurations possible. There is no only the reflectometry. So what happens? There are two kind of domains, sub-domains are there. One is the reflectometry, where you are, so this is kind of dual antenna configuration. So you have two antenna, one antenna is looking upward, is taking the direct signal from the GNSS satellites, and you have another antenna which is looking downward. So basically, you are receiving the reflected signal. You are not interested in direct signal. So in this dual antenna configuration, you have two antennas. One is for direct signal reception, and one is for reflected signal reception. And then we do and generate, go for processing the signal to generate the basic observables. Second, the most simplistic approach is that single antenna configuration. So in the first case, what happens? You are independently receiving two signals separately. Okay. So there is no need to decompose the signal. But here, what happens in the single antenna? This antenna basically just upward-looking antenna. Normal GNSS receiver, geodetic receivers, and this receiver is receiving the direct signal and the reflected signal. So this is the land. This is the direct signal. There will be a reflection coming back to the. Some of the energy go back to the antenna. So what in this single antenna configuration, you are not receiving the individual direct and reflected signal. You are seeing the combination of both direct plus reflected. So what happens? You are getting a lot of these signals. Now there are some challenges in this. So this is we call it interferometric reflectometry. So basically, what happens when if you see the interferometric reflectometry, there will be an interferometric pattern because when you know the basics of interference actually. If two signals are in phase, if you add it, there will be a construction. If two signals are in different phase, like magnetic phase shift, the signal will be disconnected. So there will be a interferometric pattern which will live with the land parameters. So for example, so basically these two basic concepts are important. Explained by James, actually space-borne things are like a dual antenna configuration. My speaker, Philip, what he explained about the ground-based strategy. Ground-based IR. It is not R, it is IR. So please keep in mind. And what are the main observables which we measure? So main observables is delay Doppler map. This is nothing but the spatial distribution of power. Because we are interested where the maximum reflection is coming back to the receiver. So we call it spectral reflection. That is called SP point. So and within the SP point, we make a delay Doppler map. That is the basic observables. Like in optical, you get a reflectance. Like in SAR, you get a backscatter. Like so here the basic observation is delay Doppler map. So basically, it gives you power, reflected power. How much power is coming from multiple points of the zone, the Fresnel zone. And there will be a single point where you will get the maximum reflection. That is what we call it spectral reflection. Then there is also one of the parameters which we observe. And basically, in the case of GNSS IR, we are utilizing S, that is called calibrated noise ratio, C by N naught. And effectivity. So basically, this is not a direct observables. This is derived from the DDM. Already there are many airborne cameras. Then now we have the receiver. So same receiver you can put in multiple platforms to get a larger scale mapping. So now regarding the first I will cover the GNSS-R, what experiment we have done from this perspective. So almost 5 years back, we have started this activity to understand GNSS-R environmental receiver. So me and my team from Graphic Data University, we have a collaboration for almost 3-4 years. One of the key members here is Dr. Sushant. He is the main person who works here in this one. So basically, we have taken a simple antenna configurations and we deploy in a field, agriculture crop field, to get how these interferometric patterns are changing over a period of time. Whenever there is a crop, there is a so throughout the cropping season, after 1-3 months, uh, we deploy these receivers with the antenna, and then we collect the signals. And every day we do the measurements using the same sensors. So by this way, we can validate what is the relation between the observables like SNR with the soil moisture. So this is the experiment we have published in IEEE 2021 for the soil. Next, yeah. So I told you I will not go into the algorithms. What it is published. So if you are interested, you can go to the publication. Again, it is read by the Sushant. So here, as I told you, if there is a bare soil actually, the crop, there is no crop. So in this first case, the sensitivity is more towards the soil moisture. But in case of you see the very high growth stage of crop, the sensitivity towards the soil moisture will decrease. So what happens if you apply the bare soil model to retrieve the soil moisture from the SNR, I mean this is IEEE, your accuracy will be very poor. So what happened? We have worked out a novel techniques to measure and remove the effect of vegetation on the this total component. So what we did actually, we used multi-path phase information as a time series variables, and we corrected the our observed SNR, and then we corrected the SNR to get a only SNR due to the bare side. And then we have and we have very good results are there. I mean, we have the more than 50% improvement in the terms of the retrieval of accuracy in terms of RLS. So this is also published in ASR, Advanced in Space Science Research. So if you are interested, go to the algorithms. The same work, I think, we also have been already told you that the previous speaker and the GNSS-R. Can you move the next slide? Yeah. So we have also developed in-house tools. So basically, what happened? The processing of Navic signals are not very straightforward. It is a lot of processing, understanding signal properties, and then a lot of sub-processing in the post-processing are involved. So what we did, we have developed an in-house tool which is called Navic app. So basically, this software is developed in MATLAB. This is basically for handling these GSM data, especially Navic and GPS. So this is again jointly developed by the SNAC and Graphic Data. So here, this software basically we import the GPS or Navic data in Linux format, or maybe you see normal formats, other standard formats are there. Then you can go one by one this processing. So this is the workflow we have incorporated in this tool. So basically, you can import. Is supposedly so there is a module to import the data in 50 format from Navic L5 to GPS and Navic S. And then you have pre-processing. So there are steps of process to do this processing and get the proper multi-path phase and between phase and peak frequency. So these are basically this is the idea observables what we derive from the after the pre-processing. Then we are also working on the multiple applications like Dr. Philip has explained to you that same kind of style observations can be used for not only style moisture. It can also give you the crop information like kind of NDVI and NMRI. You can also have in the case of crash we can have water level measurement. So we are now having built this soil moisture model to derive from the GNSS-R ground based data. And we are trying to augment this tool further to add more and more algorithms. So this will be end-to-end processing and generating the soil moisture information from the GNSS-R experiment. Go to the next slide. Next slide. Yeah. So we have in fact we have developed a in-house type and these are GNSS-R setup. So basically it's a GNSS-R setup where we have two antenna. So basically one antenna is using the direct signal. As I explained earlier that it is a two antenna configuration. One antenna is looking upward will receive the direct signal from the GNSS satellite, and then there will be a downward looking antenna which will receive the reflected signal from the ground, which could be land, which could be ocean. So this is the SAP ground, our ISRO ground sports complex ground where we have some in-house testing. So this is the complete in-house development. It's a full series of position reflection geometry information. Then ADC which calculated with receive alpha, alpha and spread out. This is the process where we generate this kind of DDMs. This is kind of DDMs. So basically we have a raw data, then we do the coherent addition integrations and generate DDM maps. This is an example of DDM maps, delay download maps. So whenever you have a peak, it means you are having this reflection coming from this zone actually. So depending on this antenna height from the ground, your Fresnel zone, the like say structural point will shift depending on your geometry of satellite and the geometry of receiving antenna. So this is one example of our development from the ground base. Yeah. So I will take a snapshot of journey of Kindle refractometry SAC school, and we have started the journey after 2015 actually. So starting with the very prototype ground-based development is a ground-based receivers with GNSS refractometry, and this is actually Sabarmati River in over the bridge, and our testing this receiver, the functional test of this receiver. Then in 19 we brought this setup to the Antarctica. So one of the lead person from our hardware, Ananya Devi, he went for Antarctica expedition and he tested this sonar depth also and get a lot of good data sets from Antarctica region. Then we tested in the ground base 2021, and finally in 2024 we have developed our own first space-borne refractometry payload for the I think technology demonstration satellites. So this is just the example of our hardware development, all the receivers and satellite packages we have developed. So it was almost more than 10 years journey to get our first GNSS-R refractometry mission in the orbit. Yeah. So now I will come to the India's first refractometry payload UPS-08 microsatellites. So basically, this is the microsatellite 2C. It's a very small bus, less than I think 200 kg or 100 kg class there. And it has, so there are two passengers. Basically, this is the refractometry antennas with the receiver in the back side, and this is the solar panel. This is another passenger or payload is called EOIR, that is electro-optical infrared sensor, especially for spot imaging of the target. So, as compared to the Cygnus mission, Cygnus, as you know, the Cygnus was the first operational GNSS payload which is still in the orbit, which was launched in 2016. And we have compared to the US rate, we have a lot of uniqueness in terms of the different parameters, resolution. So the best part, the unique part of the US rate is that land front resolution over the land, we are going to derive 1 km resolution this DDM maps, which is not in currently one of the first kind of resolution there. Thickness it is only 25 kilometers actually. So a lot of uniqueness is there in terms of the product specifications, and we are covering multiple application targets like land. We are targeting surface soil moisture, surface condition extent. Because the refractometry signals are quite sensitive to the water bodies, so we can easily detect the flooding zones. We can easily detect the water signatures for the land. Then we have ocean. We have two parameters, but we are going to retrieve ocean wind speed, which is quite important for quite essential for the ocean applications. And then significant wave height, which is very important because nowadays the altimetry is one of the tools for deriving the high significant wave height, which is also characterized in the usual rate. We have also RD application in terms of practical like snow depth and freeze thaw speed of glacial lakes, altimetry over land, these two are these four products are we are targeting. Uh, So I just go to the basics, the overview of the payload. So basically, this is the complete schematic diagram of the payload in integrated format. So this is the UIR, this is our GNSS-R reflectometry antenna. So basically, as I told you, we have antenna, downward looking antenna, which receive the reflected signal. So this is the in orbit schematic diagram. So this is the antenna which is looking forward and downward in the and covering the range of 20 degree to 60 degree elevation. So this is the so any particular point coming from this window, this blueprint will be received by. So normally what happens whenever we have a reflectometry antenna, we also need to know the location of the transmitter. So for that we have POD antenna. That is the position of the position precise of the detection antenna, which gives me the location of GPS or GNSS antenna, which is satellites. So this is the direct antenna, which is receiving the signal from the GNSS transmitters actually. So this is direct antenna. There are two direct antennas. One is looking leftward, this is another rightwards, and then this antenna gives a direct signals to get a more precise location of the GPS and IEEE satellites. I will not go into detail of this schematic diagram of the system, maybe, but overall, this will be first mission to have the capability to receive the reception from L1 and L5. So basically, GPS has all L1 frequency and then ISS has L5. So now we can receive this with the ISS and L5 data. And it's very low cost, low weight satellite. It's just less than 20 kg satellite, so we can fly whenever there is an opportunity available in the small satellite already. We can carry this satellite. So in future we are planning to have more and more number of receivers below our orbit so that we can have more depth measurements because this is only the technology demonstration mission. So we have one receiver. Next. So this is the example of actually product levels. I will just explain the. So this is schematic diagram. I will not go to explain it again. So this is the spectral reflection which is received by the receiver. And this is example of DDM actually. So DDM is digital download map. So basically X and Y axis will be down. X is the download and this is relay. And this is the what the ocean. And this is previous L1. So basically the first this is showing the DDMs on the ocean and land using GPS satellites, L1 band, and this is the DDM over ocean and land using RSS satellite. Because as you know, we have our own navigation satellite constellation, it's called NAVIC. So we are also able to receive the signals from there. So in the ocean, what happens because the ocean is very rough as compared to the land. So your power gets spread in multiple times. Like I studied, James also explained that shortest distance, if surface is rough, you get very scattered DDM peak. But in case of land, you have very focused maximum signal reflection from the land. So land, if you see the DDMs over land, always you have very good peak signal in the center, and then the background nature. This medium power basically we used to derive the effectivity. How much, like similar to the backspectrum in the case of R. So this slide shows the global coverage of daily plant passes, whatever data set we have covered. So basically, this is in the refractometry it doesn't have very definite swath. Like you have your optical camera, you have a centimeter radar. They have a good systematic swath, but in refractometry, it doesn't have a swath. It's like a footprint. There is a track. There will be tracks. So these are the tracks. There are multiple tracks starting last 6 months, starting from August. So almost the whole India has been covered. We have covered now this US continent, then South America, a lot of Australia. We have observations. So we have very good number of observations over the global target. And it is systematically covered according to decided the frequency of vision. So basically, as a science team, we define observation plan for 6 months. So we have given a different targets whether this could be covered within a time. So according to the mission, keep on observing and correct the data as per our requirements. Science team. Now the data product basically, I just explain you how the data comes from satellite actually. From satellite to the user level. So basically, whenever the data has been collected and the raw data has been collected, it passes to the data receiver at analysis the Jodhpur station. And then there will be level 0 processing, which is basically developed by the data processing team. Deployed and choose analysis. Analysis is one of the center, and science center, satellite science center at Hyderabad in this place, which is responsible for hosting data repository. So level 0 will be processed, and after level 0, basically level 0 is like very it is not a user friendly data, so it is lot of data sets are there information. So we have a level 1 processing, that is AH08, which is in the level 1 we do the processing generate the TDMs, what we have in TDMs actually. So these are the level 1 products. The level 1s are available as uncalibrated power digital programs, calibrated effectively TDMs and bistatic signal products. So this is similar to what we have further used for the training algorithms for the science surface water exchange and other things. To science we have defined, which is baseline product. We have question estimates, science question, significant wave height and land. These are 4 baseline products, which is the now being generated continuously for each tracks. Level 1, level 2 generated through the user, like through the portal, where the data will be available for the user community. So there are some silent features of level 1 data processing. I'm going to go one by one, but at least I will explain that we can see that whenever you have a receiver, it has a multi-channel receiver. So you can receive maximum 11 GPS satellites and 5 targeted given channel. So it has a 16 channel receiver. So basically, when I say receiver, it doesn't have a single channel. It can receive multiple reflection points from multiple satellites. Because all these GPS and ISS are moving very fast. Right? They are not stationary, they are also moving. So this receiver has the capability to receive 11 reflections from GPS satellite and 5 reflections from ISS satellite. So total 15 channels are there. And there are 2 types of product. One is for the question, where we have a 5 millisecond indication time, and another is the land product. Because I told you land has a 100% product. So we have very specific processing for land and ocean products. So for land, we are generating a product with a 50 millisecond integration time, which gives a resolution of better than 1 millimeter. So that is what is the uniqueness of this mission as compared to the previous mission like CDS and TDS and other missions. In Cygnus, we have a single mode. I mean, whatever data being processed over ocean, the code is processing over the land. So in the land, the advantage is not getting the resolutions are not sufficient to go for very resolution related work. So this is the first kind of data which will be available for the user community to see the effective data for the different land applications. Then we use the DEM, digital elevation models, but the effective data also get affected by the topography. So if you fly over the Himalayan region or maybe any topographic region, a lot of errors will be there due to the spectral point estimation. So we use the real time data to correct the processing and generate a error-free DDMs. Then we issue of RFI. So RFI, I don't know how many of you are aware about RFI. So it is a radio frequency interference. So basically what happens whenever we have the L-band receive reflected signal, sometimes we receive the unwanted reflection from some other targets, which is not meant to transmit. So those interference makes our data correct. So we need to identify the RFI, then go for the corrections, remove the RFI to have proper seamless data sets. So we have already some RFI mitigation process that already incorporated in the processing chain. Then the estimation of BRS and gamma, the reflectivity parameters, validation of geolocation anyway. So I will this one next to go. The level 1 data basically how it comes. Level 1 data comes in the form of different tracks. Like as I told you, one receiver is capable to receive multiple channels of GPS and RSS. So what happened? We have a very good data structure that each track wise you have a suppose I01. So this is the ID for ISS first hundred. That's GPS 03. So GPS 03 is the ID. That is unique ID. So whenever we have a reflector received from the GPS 03 with the track, there will be a proper track wise data in the level of data. So if you track wise can process data, it is from this. So this is just to give you the flavor how. Now come to the main details of the algorithms. We have in the last 5 to 6 years. Basically, the main so the major thing was to have enhanced development. First, we started with the sickness data, available data to go for algorithm development, testing, and evaluation. And because the US data is not exactly similar to the sickness data, we do a lot of model parameter tuning and refining the algorithm to match the requirement of user aid. So in this slide motion, go to the next one. So the basic electrical algorithms we have developed using the sickness data, sickness which is garden in the orbit. So basically, the basic part is that this algorithm takes the sickness level 1 data and we do processing, pre-processing based on the lot of outlier detection, data quality control. So the basic observables what we derive from the TDF is that effectivity. So it is called surface effectivity in radar resolution. Basically, radar is nothing but radar resolution which explain the how much energy you will get from a transmitter to the receiver. Basically, it is just a I will not do the detail of this one, but I just explain briefly that this is the received power. So basically, I want to calculate how much power will be received at my end if there is a transmitter in the geostationary or the geosynchronous orbit. So the wave, the electromagnetic wave, the wave travels from the transmitter to surface and then surface to the receiver, right? So this is the kind of PT is actually transmitted power. So we should know how much transmitted power is there, power is transmitted by the transmitter. Then PT is the gain of the antenna. So every antenna has a gain. You know, gain means gain. Explain this. How much you have capability to emit the energy in that particular direction. So GT is the transmitted gain. J is the receiver gain. So charge depend on the receiver gain. Then lambda is wavelength, and this is the distance between distance transmitted to surface and R distance surface to receiver. Basically, it's just a showing the link with how much wave transmit from place A to place B, how much power will be transmitted, how much will get emitted, how much will be received by us. So once these all information are available in the metadata, all already part of the data product. Then we derive the reflectivity. And now the point is that as I told that the reflectivity is not, it doesn't have different geometry. You know, you can have reflection from multiple satellites with a different geometry. Some reflection will come 10 degree, with 10 degree elevation, some will come 20 degree, some will come 60 degree. So this reflectivity, whatever we derive, it's a function of the local incident angle, the geometry. So we need to correct for it. First, we need to normalize. We need to make a irrespective of the geometry. So we do the normalization, we normalize the reflectivity, then we use the reflectivity and the map as a parameter to train the model. So we have developed multiple machine learning models starting from ANN, XGBoost, and network forest. And we have tested all three models to get the performance of all three models in terms of the accuracy level. So, and we have a standard performance statistical matrix like Pearson coefficient, bias, and RMSE and mass RMSE to evaluate the performance of the models in terms of accuracy. So this is the basic algorithm what was done using the sickness data. Now I'll show you some results. This algorithm. So basically, in a nutshell, if you have surface effectivity as a map for a given day, this is the effectivity. So I have a model for the model needs three parameters, three of them. One is from sickness and the reflectivity, Second is the SMAP PWC. So PWC is the vegetation water content. As I told you, the reflectivity or maybe signatures of the micro signatures not only depend on the moisture actually, it also depends on the vegetation and roughness. So these two parameters are taken from SMAP because there is no other source actually. Because this technique also has single observation, LSDP, we have single parameter. So to correct the vegetation effect, we need to have some ANSI data as a proxy for vegetation and movement. So we use this as an input, and then the model gives the three input and generate the signal soil moisture for a given target area. So this is the area soil moisture for the croplands. Here, this area is purely cropland soil. So if you see, the red color is the dry soil moisture condition. Blue is towards the high soil moisture. So whenever you have the red color, mostly near to the Rajasthan and especially in the Telangana state, you have a very dry soil moisture. And if you see, because the time, if you see Gangetic plain, starting from Punjab, Haryana, you see a lot of pixels are blue. So actually, it is showing the very high soil moisture condition. So this is the way we derive soil moisture from significant factor. Now we have done multi-temporal retrievals. So using this algorithm, we have generated how monthly soil moisture maps will vary. So if you want to see the spatial temporal dynamics of soil moisture over different regions, it is very important to have a multi-temporal soil moisture maps. So we have generated using this in-house development algorithm to generate a January to December soil moisture map. You see, in January, soil moisture between like 30% to 35% in the Gangetic plain. As we move from winter to the dry summer season, you see the redness is increasing. The redness of the area is increasing. You see in the April and May, lot of areas are actually red. It is in the very dry soil moisture condition. And the June also still lot of Central India, Western India are red. You see in the July, the soil moisture again started gradually increasing in this coastal area because of the onset of monsoon. And as we move towards the monsoon, the August, September, October, lot of area has rainfall, good rainfall, the moisture in this condition changes. Then monsoon depletes after the September, and the blueness of the colors are decreasing. So it is showing this is called in the winter started, then November, December, you have again residual soil moisture. So this is a picture very good annual spatial dynamics of soil moisture less than scale. Now, whenever we have derived soil moisture from satellite, we need to evaluate the performance of the model. So what we need, I will explain that there are two ways to compare as a difference. Because I want to know that what is the performance of my algorithms in terms of the accuracy, in terms of the biasness. So there are two approaches that have been adopted. One is the intersensor calibration, this comparison. So intersensor means if some satellites are already providing soil moisture, we can compare with them. Like a relative, what is the relative between our product and that product. Second is that in situ field data. So when we have in situ data, that is the best data source for validation, kind of validating data. So, but the point is that the institute data, we don't have institute data everywhere. So we have some capital facts that we have in data. So that data we have using a particular location. So using these two methods, we have, so this is the intersensor, we have compared the map for this our algorithm solution. So this is the spatial dynamics, spatial thermodynamics of R. Spatial derivative. So the R is the correlation actually. So whenever you have a very yellow and green color, it is showing very high correlation. I mean, my model is quite close to the S map in terms of the correlation. So this is for ANN model. Then we have that for RF, random forest, and XG boost. So all three are quite close. I mean, we have not observed any significant difference between three models. Normally, whenever we see bias, actually bias is very important. So if you see the bias, the blue color is like a negative bias, the yellow color is the positive bias. So whenever you see this, the blue is mostly the negative bias in terms of the Maharashtra and their dry image. So this is the way we evaluate the performance of the model. So the next statistical parameter is the RMSE. So RMSE is movement is called error. That how much what is the typical error of your retrieval as compared to reference data. So the error is basically zero. The blue means no error. It means it is good. And when the yellow color means the error is high actually. So you see, most of the dry conditions are we are having the very high error in terms of 0.1 meter to 1 meter. But what happens is RMSE is actually affected by the bias. So there is a new parameter, statistical parameter, which is standard for assessing the accuracy of the conversion is unbiased RMSE, which is this one actually. So unbiased RMSE basically we remove the bias and then we compute the unbiased RMSE to understand the performance. So typically whenever we have a low, the target is at 0.06, 0.06 should be the our target area. So not of area where good accuracy below the 0.06 target. So this is the way we have a very national level assessment of the our algorithms using English data. Okay, so this is the in situ validation within the in situ data. So we have, as I explained earlier, that we have a lot of instruments set up over the camera flights. So we do have a continuous time series measurement, and then we compare with the so this is the event. This is the site over Anand. This is Kharagpur actually. So IIT Kharagpur in the that campus we have a one soil moisture station. In this plot, from the BSM, soil moisture derived from the so this green color is actually from signatures. What we derive from the this factory data. This magenta color actually this is actually SMAP. SMAP. And this red color dot which is continuous is in situ measurement. Blue color the bars are on the rainfall because rainfall is one of the key element to change the soil moisture. So there are two ways. If there is a change in soil moisture, there are two ways. One is the either the field has been irrigated. I mean, somebody the farmer has put the water, or there is a rainfall. Otherwise, there is very less change in the soil moisture. So we need to verify whether the rainfall is there or not. So if you see this is the monsoon period. Starting from July to a lot of things there in Kharagpur. Before that, the April also a lot of rainfall. So whenever there is a rainfall, actually, the soil moisture jump. And similar trains are out there. We have observed our thickness measurement. And there is a very good difference between the spectrometry and SMAP. Because SMAP is a resolution detector. So what happened? It gives a very coarse. It will get saturated for a given time. Within this July to October. There is no change in SMAP. It should be fully saturated. But if you see the green color from the spectrometry, it passes very within that time limit. And it is quite match with the whenever there is a peak in the institute, same peak is reflected in the spectrometry science. So this gives a very good understanding about this. It is following very good trend with the institute data. Also the accuracy we have seen. Similar way. So this is the case of IIT Kharagpur. I mean, the Kharagpur I just like eastern part of the India. Now we have one more station at Anand, in the western Gujarat, near to Ahmedabad. Anand district is there. Might be familiar. So Anand, we have very good setup. It comes under a semi-arid zone actually. The average rainfall is not very high. So here, if you see the variability of soil moisture is not very high. So if you see the green color is following with the this pattern. And whenever there is a rainfall, actually, you see the density of the rainfall, which is quite higher in case of Kharagpur. But in the Anand, we have some bar chart, which is the rainfall around maximum rainfall is 200 mm. So this rainfall, whenever there is a rainfall, actually, you have a peak. This peak is matching with the rainfall. This peak showing that there is a sharp jump in the soil moisture. So there is a very good trend. Also, we have observed in the over the this institute side. Gray area also is there, and not gray area actually constant of the field data because there is an issue with the institute measurements. Because what happens whenever we install a soil moisture sensor, because soil moisture is high variable, especially and temporary. So basically what happens within a meter, you can this institute data is quite varied for within a meter. Within a meter, if you have a but the Cygnus and this refractometry and SMAP, they cover a large area. So always there will be a scaling issue. The speeds are different. So if you see here, so you see this one actually. This is almost flat here, the green, but here the jumps are there. This jump, actually this jump is not because of rainfall. That's why I put a quote. I put here. What we need a rainfall because we go for direction. There is a jump in the soil moisture. But there is no rainfall. So what is the result? Any guess? No, soil moisture changes. Soil moisture is a peaks are there actually. So basically these 3 points are basically this is a crop land and the field has been irrigated with it. So we have verified with the local party. So these fields are basically, but what happened? Only that field is irrigated, not the whole area what is covered by the supply. Okay? So here you see the go back. So here what I want to explain there is a difference between in situ observation and sunlight. So always you keep in mind whenever you are going to validate the sunlight direct moisture, you have to keep in mind for a given sunlight pixel how much area it represents. And you should have a field average of that pixel, then one you can compare. Directly just 1 point within a pixel is not representing the whole area. So that is the way we have standard protocols. We have defined the standard protocols how to validate the protection moisture product using the proper optimized field measurements. Okay, now let's go to the next. Okay, so we have also done some kind of uncertainty analysis based on the models. If there is some error in the reflectivity measurements, how it will impact on my interval accuracy? I suppose I have a model, but the model also has some errors. So we need to understand before going for algorithm interval that if there is an error in data in the reflectivity, whatever I got from secondary observation rate, if there is a more error, what will the uncertainty in my interval? So for that actually we have done Monte Carlo simulation, and we have done millions of simulations to understand that to achieve a 4% accuracy level, what is the maximum error I can tolerate in the reflectivity measurements. So this is the number, basically this is the part of our sensor definition studies. So in this we do before the actual development of algorithm. So we need to, so every mission will be defined that this much I need to achieve. Then only we can say okay, this mission is successful. Okay. So to understand this sensitivity, we do this sensitivity analysis, and we modulate this. We add the errors in the reflectivity, and that's the particular by error in the retrieval of the model. So here you see, for this is the RMSE behavior retrieval. If I increase the error detection in reflectivity, the errors of reflectivity is increasing, my errors are also increasing. The different soil moisture condition. So this way I can understand that the error also not a single number. It also varies with the soil moisture range. In the dry soil, I have more error in terms of the wet soil or moist. So those understanding are quite useful to understand the retrieval algorithms and how to improve the efficacy to consider all these variability. Okay, so whatever we have done the algorithms in series data, we have implemented for our own algorithms, our own ES08 GNSS-R payload. This is the actual implementation. So basically, we are taking GNSS-R level 1 data as anything format. We extract data, we have an effectivity, local engineering, all the geometry parameters, because I told you geometry is very important. We are not using, we are used to have data quality flags to remove the impractical numbers so that you can have very good training. Effectively by using local engineering, then you put the layers tab, and then this is the data from SMAP. So SMAP, we are using 2 parameters. Basically, it is needed to correct the measures effect and roughnesses. So we create a global mojang, and then we make a layer stack, we apply the model, then generate the typology map, and that is because level 2 impact the data, impact the level 2 whether level 2 product for the user. some of the trivial on this. So this is one of the examples of the how the GNSS-R centimetry level 1 data looks like actually. So it doesn't give you image, it's a purely non-magic sensor. So you have the tracks. You see. So this is the track. This is the track of GPS05 and this is the track of GPS02. So basically this is almost crossing the null signal here. This is Ahmedabad, this is here almost. So this is the effectivity from level 1 data. Now, so in terms of dB, the power, then second is the after applying the model, this is the soil moisture level to soil moisture for each track. We are doing track once retrieval, whatever tracks are there for this satellite. Because each satellite has different geometry. We cannot remove all the tracks and then go for retrieval because we have to do track wise retrieval, without combining. This is the first data actually. This is our first data. We acquired over the African region, North African region, very Sahara Desert. Now the service. So this is the reflectivity. To see the whenever the yellow color is the dry slow reflectivity. So anybody can tell me, I give you one example that the low moisture condition, what you expect and what reflectivity of expected high condition. So low or what should be the reflectivity in case of low soil moisture? It should be low because I told you that low soil moisture, low refractive moisture is low reflectivity. Similarly, this is a purely desert region. This yellow color with the low reflectivity. And similar here, you see the soil moisture over this one is low actually. Our model is giving very good time frame more than the first data what we have processed generates soil moisture information from this data. This is first validation of our ensure the quality of the retrieval. So what we did, we compare with the snap with the same area, same day and same track. And we compare with the this is the one track of the this blue color showing the US direct fire moisture and this red color showing the snap fire moisture. And we found very good trend. I mean, we are quite well matching the snap data that gives you confidence that our retrieval algorithms what we have developed for the issue it is working quite well. Any question on this? Shall I move forward? Okay, this is another data, another track which is passing through the Maharashtra region. This is the histogram of DDM-SNR. The SNR is from 0 to 20 dB, and reflectivity. Anyway, I will go to track. This is again another track on the 21st August. And this is the soil moisture. You see the soil moisture is very high. The blue color is high, the yellow color is dry. So here you see the reflectivity also. So basically what happened, this is the date is 21st August. It is the almost monsoon season. So all these areas are basically almost saturated soil. So that's why we are getting very high soil moisture in this area. So whenever we analyze data, we have to keep in mind as season, what kind of seasons, what will be the expected soil moisture range we can get over the this side. This is the one of the track we got from western India to the north of India. And we have repeated this river also similar here. So see, when the track is there, it is like one footprint, one like point is there, similar point. So see, it is covering a lot of different land properties. So a lot of variability there in the data. Similar thing, if you see the dynamic range of soil moisture, it is almost covering full range from 0.5% to 65% soil moisture range is covering. Here the reflectivity also covering very good range. So these are the type of data what we have access to periodic. Similar by verification with the SMAP also here. So this is the green one is the SMAP soil moisture. At 9 km, and this red is the actually our 1 km soil moisture information as a trend. You see now there is very good trend matching, but there are some lot of variations are there. That is because of resolution actually. Because SMAP gives a 9 km resolution. Within that it is a yellow soil moisture. But if you have a significant activity, this is where you can get much finer cell motion. So there are a lot of variations within an 9 meter, which is from here. So based on that, we have developed processor. So basically, whenever we have algorithm developed, we need to develop the processor to generate the map regularly. So this is the automatic operation of motion processor. So we take 08 data as input, then LC data is the operator. Then we need to find we processor will take the input data, do the error handling, data quality control. We do a lot of quality control processing, then model, then output will be generated and saved as it. This is a simple workflow for the operation of motion processor. Okay, so now this is the current global coverage of last 6 months data from August to January 2025, and this is the whole India almost covered by. We have very good observation about the Central African regions. Very good number of data available over the this news continental, north and this east and west continental. Then lot of observations we have over Amazon. Because this South America region, because one of the objectives of our indentation actually, we have to map where what bodies are changing. So based on this global, we have cosmic global retrieval. This is the cosmic global soil motion map of all the tracks from the last 6 months. So you see, and I will explain you that it can be very, it is picking very good variability. In fact, this African North is totally dry because it is mostly Sahara, right? So it is totally red means dry soil. We have Gulf countries. Again, these tracks are very low. The best example is the US continental. In US, actually, you see the east and west coast. The east coast is mostly actually quite high soil moisture because of a lot of things, and then western part is mostly dry because of this is mostly very rainy scanty area. And we were also lucky to get one of the cyclone-driven rainfall over the Florida region. So you see the blue color is just totally flooded actually. So that was one of the cyclone came hurricane came in that time in the last year, September October time frame. One of the examples of the Australian continent. In Australia, basically most of the 90% are mostly the barren or desert land, right? But there is a Perth area. If you see the western part, there is a Perth area where a lot of cropping is done actually. So there the soil moisture is very good in the range of the mid range. Similarly, if you go to India, this is the covering the whole monsoon season from August to the January. You see the Gangetic is mostly medium high soil moisture. Yellow color, blue color, and then light blue color. The Rajasthan part is mostly dry. And then if you see the Eastern Ghats region, there are also a lot of moisture. So it is in absolute term also it is coming very good trend, very good specialization is picking up. So this is this product will be commercially available soon from the user community as a level product globally. And we are expecting that within 6 months again we will cover the whole this cosmic global coverage from 37 to 37 degree latitude actually. Complete coverage will be there. So now come to the validation. So what happened? Earlier we did this track file validation, comparing the map data to know the quality of the issue drive side motion. So we have again compared with the track files. So for this track, like suppose this blue color is the 310, that is the GPS data, GPS track. Then we also have some good operation from ISS data. So this African continent tracks have some GPS, some ISS tracks. So we got very good accuracy in terms of the snap, and this is the numbers what we got from unbiased RMC is better than 0.08, which was our target to get a operational product. So one of the observations is that the initial data is quite good from the estimate, and we got very good validation results, and the quality of data we found are quite good matching with the existing snap and so this is all from my side. Next. Okay. So thank you so much for I any questions there? Yes, yes. So you see, the data already whenever we have a satellite mission, there is a need for processing phase, and then so we take some time to make all the corrections and develop the process and everything. So currently we are doing that phase almost within some time. Shortly we will open this level per data collected products for the public. A data set will be available through the only portal. Yeah. If you are suppose if you are again need of data sets, single data is publicly available. So there is no lack of sample data. Because we have also exclusively used the single data for research development of algorithms. So I would suggest you to go with the available single data also. And soon the USD data also will be available for the testing evaluation.
Thank you so much for the wonderful presentation. I just wanted to know about the proposed starting against Ananya and went in. So could you please elaborate more on that?
Yeah. So actually we have a expedition and there will be a team from ISRO where we will scientific proposals. So I remember in 2019 or 18 we went to Antarctica with this kind of receivers. So basically what happened, the idea was that the Antarctica itself, a lot of multi-layer placing zones in there. So normally what happens, either you have a some kind of a field expedition with kind of a core sampling, so that is very cumbersome actually, and also it takes a lot of effort actually. You have to really do the sampling, detect the these ice layers or multi-layer stratigraphy. So because this data automatically has a purely non-destructive method. I mean, you need not to go and do the sampling, right? You just get a reflection and based on that you can have multi-layer reflection. So there will be a Antarctica, we have a snow cover, right? Dry wet snow cover, and there will be a multi-layer ice. So multi-layer ice kind of a ice snow deposit at multiple times. So there will be a multiple layers, static layers. Okay. So this static layer is a different reflection. So he did a very good experiment. He collected the data. He has already demonstrated that at what depth we are getting L-band reflection from that which layer we are building it. So almost it went to almost 100 meters for L-band. I don't know whether he has published or not, but they were very good observations. But doing the field work in Antarctica is very harsh environment and very challenging task.
So it was a wonderful talk, and I'm glad to witness this. The question is, what was the reason behind choosing Antarctica over Arctic? Is there any possibility that the similar kind of observation can be observed over Arctic region?
Actually, so basically, Arctic also we have expedition every year. But Antarctica has different ecosystem. So Antarctic we have also we have Arctic administration and Arctic also we have. So degree and administration for both the poles, not just Antarctica. Antarctica we have also knowledge of there. We used to see the data separated from Antarctica. Not there is no specific to choose Antarctica over Arctic. But both are we are from field expedition.
GNSS-R configurations, one of the main upcoming parameters is signal to noise ratio. Yes. Basically, SNR has significantly can be affected by the weather parameters like weather obstructions and interference. So it can lead to the measurements of signal. So how can we be aware?
So, yes, I agree that the microwave is not totally free of the public effect. But you see that if you consider the L-band response for the atmosphere, we have cloud, we have aerosol, we have gases elements. The L-band wavelength is around the wavelength of L-band is around 22 centimeters. So at the L-band, we don't expect any much changes because of atmosphere. Yes, because my ionosphere, what happened? The ionosphere, because of the ionosphere content, there will be delay in the receiving the impact. So, but that might affect the accuracy level of position accuracy. So, in navigation, that is the biggest challenge of having the answer delay. But for the refractometry, that may not have a heavy impact on, because we are not considering about the position accuracy. Okay, even though if there is 1 or 10 meters, if my Fresnel zone, I mean the affected points, it might be okay for me. But if you have a position accuracy, if you are going for navigation applications like I am going for my location, it will be error because of atomic delay, which is typically 4 to 5 meter actually. Atomic delay is one of the major constant. So there will be a mitigation technique like if we use the 12 frequency like ISS, we have a L5 and S. Using 12 frequency observations, we can compute the delay and we can correct the data. So there are multiple ways to mitigate this delay to improve the accuracy, position accuracy. But as far as the factometric is concerned, I think it doesn't have much impact because of the understood delay. Thank you, Dr. Pandit, for the insightful and information session on GNSS-R in soil moisture. We'll now break for lunch and reconvene at 2 p.m. For a session on mission implementation and cooperative by Mr. Sachin Babu. Thank you.